Welcome back, everybody. I hope you're doing fine. I just want quickly to say something about today's topic. So we are going to continue along this line of discussions about harmonic oscillations. And this is going to keep us busy till at least 1 week after spring break. Now, one of the things you probably have seen, I don't know how much time you have to look at the midterm, is that the midterm is actually a kind of exercise on looking at potential surfaces, calculating the forces from the potential. And then when you have the forces, you can find the acceleration. And then you can predict by looking also at the potential surfaces on how a given object is going to move. So even though there are 3 exercises, they are pretty similar to each other, but there are different types of potentials which the object moves in. And this is a very common situation in physics. And you're going to encounter that when you do electromagnetism, when you do statistical mechanics, when you do quantum mechanics, you will see similar problems. And so the kind of idea is to allow you to develop your intuition. And then when you have looked at the potentials and you figure out roughly how the system is going to behave, you will see both from the analytical paper and pencil calculations and the numerical work that this is actually what you expected. So the examples today are also going to be lookalikes of what you see during the midterm. We are going to use Friday to midterm discussions only. And next week, we will most likely also use parts of Wednesday and Friday for the midterm discussions, so that hopefully everybody will be done before the midterm kicks in, so that at least you get 1 week of rest, which you need. But the semester is pretty hectic, isn't it? So let me just quickly say, remind you of where we were on Monday. So the topic now is to look more at the mathematical pendulum. And then we are going to move into what's called damped motion. So the nice thing with the harmonic oscillator is that it's so simple. And it allows us to numerically solve it very easily. And you will see that the program which we end up writing is extremely simple. And the analytical solutions which you also can get, they are very, very useful because they illustrate mathematically what is going on. So the harmonic oscillator is one of these systems which we as teachers love to teach because we have nice analytical solutions. And by looking at the motion, you can actually go back to the mathematics and say, hey, that makes sense. This means also that we are going to revisit some relations between the exponentials and sine and cosine functions, which were part of the first exercise and the first assignment which we had. So now we are going to actually need these relations between exponential functions and sines and cosines. So this is going to be part of the analysis which we're going to make. But let me bring up one of the examples of harmonic oscillations, which you probably have seen before, and that's the mathematical pendulum. So let's just go through the mathematics and see that we get the equation which I promised on Monday. And then we are going to look at damped motion and see what that means and see how we can solve that analytically. Okay, let me just switch over to the whiteboard here. And let's go through some of these details. Let me just bring up my whiteboard here. So on Monday, where we ended was to set up the system which we were looking at, and that was the mathematical pendulum, where we had an object which was fastened to a roof or wall, and then it had a rod which was a so-called inflexible rod. It stays, it's not being deformed, it just keeps its length. And then we have this object which oscillates back and forth. So let's just remind ourselves quickly about the system which we had. So this is normally called, when you go into textbooks, it's called the mathematical pendulum. So we have this could be the roof, or the ceiling. And then we defined an origin here. And then we have the x-axis along here. This is the x-axis, this is the y-axis. And then we have this object with a given mass, m. And then we have a rod of length r, where r is the distance from the origin till the mass here. So this r is now defined by this vector here, r. We have an angle phi. And then we have obviously the gravitational force which acts on the object. And then there is some kind of tension, which actually is the force which actually keeps this mass attached to the rod. So we just label this with a T here. Now, the first thing we will do now is to define the forces which act on the system. So we have taken away any kind of air resistance. So we are just assuming that there is a gravitational force and this force which keeps the object attached to the rod. And we are neglecting the forces from the ceiling and so on. So that means that the forces we are looking at is just a T, which now would be equal to a magnitude T. Let's just call it this a magnitude times sine of phi. And this is multiplied with the unit vector in the x direction. And then we have plus a T times a cosine phi times the unit vector in the j direction. So this is again one of these basic steps which we always make, where we analyze the problem. And these are the forces which are at play. And then we need the gravitational force. And clearly then depending on how we define, where we define the negative or the positive y direction. So if we now stick to the standard definition which we've had, this will be given by m times g multiplied with the unit vector in the y direction. So you can make it more sophisticated and you can add a air drag. You can add more forces to it, but this is the simplest possible mathematical problem. Now, the equation which we are going to derive is a pretty famous equation, but let's now see how we can manipulate these equations here. So if you look at R, and we keep an eye on the drawing here, so R would typically be given by L times sine of phi, so that's the length of the rod, multiplied with I, so that's the position, and times L of cosine phi multiplied with J. Does that sound pretty okay? It means then that if we take the force in the y direction, so we can now write the total force, that will be given by T times a cosine phi plus this N times G. Sorry, it should be a minus N times G. And then we have in the x direction, this is the force acting on the object. In that direction, that is a T times a sine multiplied with phi. So sine of phi. Then, since we know that the force, if we now take the mass of the object and look at the derivative in the x direction of dt, this is supposed to be f of x. And obviously, if we do the same exercise in the y direction of dt, then we have f of y total. That's the total force. So the thing we need to look at now, since we have a motion in the x and the y direction, one of the quantities we need is to calculate d of r of dt. This is going to give us the velocity. And we need the second derivative. So if we take the first derivative of this quantity, and we go back to the equation we have for r, we see now we have to be a little bit careful. So we're assuming that L stays the same. It doesn't change with time. So the quantity which changes with time then is the angle phi. So when we take the derivative now, we need to use the chain rule because we have a sine phi and a cosine phi when we take the time derivative. So when we take the derivative of r with respect to time, this is now going to be equal to L. L stays the same. And then I obviously have a d phi dt. and I take the derivative, so this has to become a cosine of phi, and then I have my I direction, and then I get a minus sign because I had a cosine there, so I get an L times d phi dt of sine of phi multiplied with the unit vector in the j direction. So this is just an application of the chain rule. And we know that the only quantity which changes is the angle phi, because we have assumed that the length of the rod stays the same over time. So we have the first derivative, but since we want the forces, we actually need the second derivative with respect to time. So now we need to take this equation here, because that's going to give us the acceleration. And so we just simply need now to calculate the second derivative, what we have. So that means that we have a new application of the chain rule. And we need now to take the second derivative of phi, but we need also to take cosine phi and sine phi. So we're going to get two more terms here. So if we do that, we will get the following. So we're going to get an L, which stays the same. We get the second derivative with respect to time of dt, and this is multiplied with a cosine phi. And then I have a minus L, and this is multiplied with a d phi squared. And then I have a sine of phi. And this is the x component. And then finally, I get a plus, and I have a minus of L of d second derivative multiplied with sine of phi. And then it's minus L, so let's just write it down carefully, of d phi dt squared multiplied with cosine of phi. And this is finally multiplied with the unit vector in the y direction. So this is the second derivative. And now we can go back to the forces which we have. So we have the force in the x direction and the force in the y direction. We know that this first component, which you see, the one which is multiplied with the unit vector in the x direction, this is the acceleration in the x direction, and this is the acceleration in the y direction. And then we can obviously set that one equal to the expression we have for the forces. And what we're going to do thereafter is just to do some small manipulations. And with some small manipulations, we are going to get to the famous equation for the mathematical pendulum. So let's see how we can get to that final expression. And that expression is actually an example of one of these very, very famous cases of harmonic oscillations. We are going to see other types of examples later. Actually, for those of you doing electromagnetism or electronics, you can take a circuit with a resistance, an inductance, and a capacitance, and you're going to get the same type of oscillatory motion. And that's actually quite interesting. Okay, so let's just go through some of these basic steps. So the next thing we're going to do now is simply to say that the force in the x direction, f of x, total. And if I now divide by m, or if we just keep m here, so this is going to be given by a sinus of phi. And this is clearly equal to the acceleration in the x direction, m times a of x. So that becomes simply m times L of d of phi dt cosine phi minus L. And then I have my d phi dt squared multiplied with a sine of phi. So now I'm not putting in the unit vector in the x direction, because now I have actually broken it down into the component x, and then I'm going to do the component y slightly thereafter. So this is the force in the x direction, and then I have a similar one for the y direction. And we know that in the y direction, this is given by this t times cosine phi minus mg. And this is equal to m of minus L of d of phi dt, the second derivative, sine of phi minus L of d phi dt squared. And this is multiplied with cosine phi like this. Now, this looks pretty ugly and messy. But what we can do now is to reshuffle a little bit these equations. And one of the things we're going to do now is to see that we, by some simple reshuffling, we are going to get two right-hand sides which are the same. And then we're going to take this equation when it's being reshuffled a little bit, and the same with that one, and we're going to subtract them. And by that subtraction, we're going to get rid of many of these type of expressions, which looks pretty nasty. So this is what you're going to see now is a kind of pretty standard trick, which we often do when we manipulate equations. And so let's see how we can actually do that. So one thing which I'm going to do now is to take this expression for x. If you look at, let's frame this in, this one. And I'm going to multiply that expression with sine of phi, both the left-hand side and the right-hand side. And then I'm going to take the other expression, the one for the motion in the y direction. And I'm going to multiply that with a cosine phi. And if I do that, I'm going to get the following expressions. When I reorder a little bit, I'm going to get a n times L. So this is just reordering the equations of dt. And since I'm multiplying the first one, the x equation with sine, I get a sine of phi minus mg times sine of phi. And this is equal to a t plus n times L. And then I have a d phi dt multiplied with a cosine phi and multiplied with a sine of phi. So that's the expression in the x direction. And then I take the expression, the next one, in the y direction. And if I take the one in the y direction, what I have then is the following. So then I get a, so let me just rewrite that one. Now I just have to remind myself of what I did here. So I think this one was actually, let me see, so I didn't confuse myself here. Yeah, actually, this one was the one for the y direction, and the one for the x direction is actually this one. Sorry. So I actually was reading the wrong line here in my notes. So the expression I have here becomes equal to a t plus an ml times d phi dt. And this is multiplied with cosine phi times a sine of phi. And then these expressions here, so this actually has a minus. Then what I'm going to do next is that I'm going to subtract, no, this has a plus, and this comes with a minus. If I now subtract these two equations, so subtracting these equations, then what you see is that the left-hand side disappears. No, the right-hand side disappears. And when I put everything together then, what I get is that I have ml of the second derivative, phi dt. And then I have a cosine squared of phi plus a sine squared of phi. And that's going to be equal to n minus n times g of sine phi This equation which you see here obviously leads to 1. So when I bring everything together, then and divide by n and l on both sides, then I get the famous equation for the mathematical pendulum, which is given by minus g divided by L of sine of phi. And then it's common to introduce a new frequency, which we call the angular frequency, or we can call this for the natural frequency because it's given by a natural constant divided by the length of the rod squared. So that means that I have an equation now, which is given by a d of phi of dt equal to minus omega 0 times a sine of phi. And that's the famous equation for the mathematical pendulum. Now, what you can assume then is that phi is much, much smaller than 1. And then we know that sine of phi can be approximated with phi. And if we do that, then we have a standard equation for an harmonic oscillation, which we now have seen several times. Minus omega 0 times phi. And that's the standard harmonic oscillation equation, which we know the solution to. So that's given by a sine and a cosine. The full harmonic oscillator, if you now don't assume a small angle, obviously has the sine of phi. And this is a little bit more tricky to find the analytical solution of, but it's so simple to program numerically. So this is one of these cases where you now see the kind of similarities when you have reduced equations between harmonic oscillations and physical systems like this mathematical pendulum. Now, the equations here are equations which we're going to encounter a little bit later. But what we are going to do now is that we are going to look at the addition of a new term to the harmonic oscillation. We're going to look at a damping term. So we are now, instead of having a pendulum or something which is attached to a spring, which oscillates back and forth, we are going to damp the motion of the object. So let's see how we can set up the equations for that. And then we are going to look at how we can program it. And based on the results you get, you can actually ask yourself, what does it mean? What is happening here? Why do we get this specific behavior? And when you have that, we can actually move on and find the analytical solutions, and then go back to what we observe when we solve the equations numerically, and then infer from the mathematics what is happening here. And this is what we're going to do now. So we're going to first set up the equations. We are going to solve them numerically and look at the solutions. And then we go back to the mathematical exercise in finding the analytical solution. That's the kind of path we're going to take now. But this is just an example of many of the types of harmonic oscillations which are going to meet in science. So let's now move to the more interesting case, the more realistic one, the case with damping. So if we do that, and then we take a mathematical intermezzo a little bit later, but let's now look at the case with damping. And let's go back to the plane harmonic oscillator. So what we had in the plane harmonic oscillator in one dimension was an equation here where we have the acceleration. And then what we had was a minus a k of x. This is the one-dimensional case. There is no problem in doing 2 dimensions or more dimensions. That's just a slight complication of life. So we're going to stay in 1 dimension because the basic physics is already displayed in a 1-dimensional case. So if we now rewrite the equation here, so not that one, d of x, dt. So let's rewrite it. And then I'm going to leave an open spot here. So I have a plus k of x equal to 0. And I'm going to add something here. Now, if you go back to what we did in the very beginning of the semester, and you think of the way we added this air drag, we could add this air drag. So remember that the friction or resistance which we have, there is no fundamental law in nature which gives you a nice neat mathematical expression for the force. Keep also in mind that the harmonic oscillator, which we derived, was based on a Taylor expansion around the minimum. So everything we're doing now is a model, right? So if you were to add resistance here, suppose some friction. So you have a thing which is sliding back and forth, and you have the spring, and you are thinking of adding, let's say, some friction. So how would you model friction here? If you think back of what we did with the falling object. So, yeah.
Maybe set up some sort of conditional statement to check if it's like position is touching the ground or touching an object,
yeah,
so that you can apply this extra force.
Right. So how would you think that extra force would behave mathematically if you want to frame it in a mathematical way?
Isn't it like a coefficient times the normal force? Or
it could be that. If you now want to make it even simpler, if you suppose you want to make a model for the normal force, right? So if you're thinking of friction, so you have this thing going back and forth. So if you think of one of the quantities you have, like, so we have acceleration, we have velocity and position. So how would you think this friction would behave? Just think back to the air resistance in the air, yeah? Yes, the velocity times a constant. So that's the simplest model we can make. We don't know whether that is a correct model, but we can say that we assume now that this block is a dull block, which is just sliding back and forth very slowly. And then what we see from experiment is that often this friction can be modeled as something which is proportional to the velocity. When we looked at this air resistance with the object falling, depending on the velocity it had, it could go like velocity squared, or just as a velocity times a constant. So we are going to have to simply assume that this moves, the friction is something which is given by the velocity times a constant. That's the simplest model we can make. So we are going to put in something here, which looks like this. So we have a B times d of x dt. So that's going to be our new equation now. Yeah. So in this case, we assume that it's moving slowly. And what you often see then is just proportional to the velocity. Yeah, just a linear. You could add more complications. So suppose you actually run an experiment. What you could do then is to add other types of terms here. You could have a velocity squared times a constant. And then you could ask yourself, is this meaningful? Does it reproduce data better than just a linear velocity? So we don't know that. So this is just the simplest possible thing we can make. And then clearly, having these kind of tools, you can always go back to experiment and see if that fits experiment. Okay, so let's rewrite this equation a little bit. So when we did the harmonic oscillator, what we did was actually to divide by m. So we had this definition of omega squared, which was k divided by m. So we are going to get rid of some of the constants. So we get d of x dt. This should be the second derivative, by the way, plus b divided by m of dx dt plus this omega squared times x equal to 0. So this is the equation which we are looking at now. Okay, so one of the things which is extremely useful, as we did in homework number 5, is to scale the equations. So one thing we could do now is to try to get rid of these constants so that the equation we look at looks even simpler. And you will see that this is not something you do only when you want to solve it numerically, but you also do it when you want to solve it analytically. Like in this case, we have a natural angular frequency, which is given by the constants of the system. But what we could do now is to say that, hey, maybe I would like to have a time which is dimensionless. So you can do that. So now I want to scale away some of the constants by defining a dimensionless time. And the way I do that, since we know from last time that this frequency goes like 1 over time, I now define a new constant, or actually a new variable, which I'm going to call for dimensionless time. And let's call this tau here. And that's going to be given by this frequency multiplied with the original time. And you see that this is dimensionless because our frequency goes like 1 over time. We multiply with time, and that has no dimension. So what we're going to do then is just to reinsert it back into the equation here. So we just manipulate the equation a little bit, and that's going to give us a simpler equation to deal with numerically, so that when you're going to write a code, the numeric simplifies considerably. The thing which is nice here is that actually you can replace x with the charge in an electric circuit. And you will get exactly the same type of equation, except that the constants are going to be different. So that means that if you have a program which solves this type of equation, you can actually look at oscillatory motion in a so-called resistance, inductance, capacitance circuit. And that's pretty neat. So when you come to electromagnetism, you have already a program which can solve a typical case which you encounter in that course. So let's bring it back into the equation. So I'm going to plug in now. So this means obviously that T is equal to tau divided by omega 0. So I plug this back into the equations, and that means that my equation is going to look like a d of x, but now it's the second derivative with respect to tau, plus a b times n multiplied with a w0, and then a omega 0 of d tau plus omega squared of x equal to 0. Now, that doesn't look like a simplification, but now we just divide by omega 0 squared. So if we divide with that one on both sides, and obviously we're assuming that these quantities are not 0, so we can now rewrite it, plus a b divided by n, and then we get omega 0 of d of x of d of tau plus x equal to 0. Now the equation looks much simpler. Then the final stage we do now is that we simply replace this quantity here with a new constant. And in this case, the constant, by historical reasons, there's a factor of 2 here. And I never remember why. I always have to remind myself why there is a factor of 2. So it's common to define a gamma, which is given by b divided by 2 of n of omega 0. And then if I plug that in, then my equation looks a little bit simpler. Plus a 2 times gamma, and then I have a d of x of d tau plus x equal to 0. Now, originally, when we set up the equation, we had an expression for the force, and then we divided by the mass. So then we just had acceleration. And you know that the acceleration is length divided by time squared. If you look at the final equation, which you have here now, so let me just bring it a little bit up. So the final equation here, this is the one we are going to solve numerically. So if you look at that equation, what is the dimension of this equation here? Is it mass? Is it length? Is it time? So if you look at it, so time is now dimensionless. There is no dimension there. So if somebody asks you with this x, when you're solving the equation, what does it come out like? What is its dimension? Length, right? Just length. So we got away of all the other constants because we started with the acceleration, which is length divided by time squared. And now we got rid of time. So that means that we're just left with length as a dimension. So this is a typical equation which you are going to see tons of times in physics. And harmonic oscillations are something which pop up almost everywhere. You make this approximation, you look at small changes around the minimum of potential, and you add some friction, and then you have an equation like this. If you go to this electric circuit with a resistance, inductance, and a capacitor, you're going to have an equation which is almost a lookalike. The only thing which is going to change are the physical constants. So what I'm going to do now is actually, before we solve this, this can also be solved analytically, but we need some math. I'm actually going to jump into the code first, and then we're going to try to look at what we see and try to understand what happens here. And then we go back to the mathematics. I hope that's okay, because I want to trigger a little bit your intuition here before we move on to the mathematical exercise. So this is the basic equation we're going to look at. And let's take a look at the coding here. So let me bring this up. And so that one, so the Jupyter Notebook. So what you're going to see here is the code for this case. So this is a one-dimensional problem. And you will be surprised by the simplicity here. And what you also have here, there's another reason why I bring it up, is that this is pretty close in exercise 1 and 3 in the midterm to what you guys are going to end up doing. So in a certain sense, you almost have the coding part of the midterm in this extremely simple program. So the first thing we typically do now is to define some initial things. We want a final time, 20. This is dimensionless time. We fix the initial arrays for velocity, position, and time. And then we give some initial conditions. So in this case, we have an initial x of 1. We give a 0 velocity. And now I'm going to set up this parameter gamma, which you have in the equations. And we're going to play around a little bit with different gamma values. So let's now just run the code here. Sorry. So I'm going to change this gamma a little bit. So let me just put it to 0.5. And if you look at the code here, this is the essential part. So this is my acceleration. This is just gamma minus 2 gamma times v minus x. So keep in mind that if you go back to the equation we are looking at, we have the acceleration, and we have to move the 2 other time terms to the other side of the equation. So that means that the gamma comes with a minus, and then we have a minus x. You see, this is extremely simple. This is the acceleration. And then what I've done here is actually to use Euler-Crommer's method. So there is a simple, in the velocity here, I use the updated velocity to calculate the position. Now, let me ask you one question before we move on. When I now have this friction term, what is your intuition about energy? Will energy be conserved or not conserved? Why?
Friction is dependent on the force.
Exactly. And you're going to dissipate energy due to friction. So if you now were to look at energy conservation, energy will not be conserved here due to the fact that you have this friction. And actually, if you run the calculation, you would see that. So this is an example of a non-energy conserving system. Obviously, total energy is conserved, but then we would have to add the surrounding as well. And we would have to have a pretty good model for how the surrounding absorbs energy. So if we now run the code here, let's just do that. And let's see what happens. Now, let me just make this gamma a little bit smaller. Just let's do that. Now you see something like this, right? So we started at 1. So if you look at the figure here, what is happening? If you just use your intuition, right? So this is the motion. So we plot the position as a function of time. So what happens? Say it again. It's dampened, exactly. So we see a clear dampening. We see this kind of oscillations still, right? But then it gets damped, and at a certain point, it comes at a certain time, it stops up. So if I'm making this damping term weaker and weaker, smaller and smaller, what would happen then? What is your intuition about the motion which you would see if you make the damping smaller? Yeah?
It'll oscillate for longer.
Yes. So we will see a much more clear oscillation. So what you see here now is a kind of envelope where the oscillation becomes, you have an oscillation, but there is also damping. So if you go back to what you have seen in mathematics, which function would cause the oscillation? If you think mathematically of it, if you want to describe something which oscillates in a boring way, and it looks the same all time. Yeah? Yeah, sine or cosine. So what you could say now is that in the solution here, when we're going to derive the analytical solution, is that there will be a cosine sine part, which will give the oscillation. And if you're now thinking mathematically of what kind of function would be ideal for damping? Yeah, an exponential. An exponential with a negative argument. So you could now think of intuitively now, without solving it mathematically, and this is what we are going to see, is that the solution is going to be probably a product of a cosine and sine, multiplied with an exponential with a negative argument. And this is what we're going to see when we do the mathematical exercise. This is actually pretty well described in Taylor 5.4. But I wanted to take this kind of route here just to trigger your intuition and see when you just look at things here, by just looking at the graph, what would you expect? So let's change these parameters a little bit and just repeat some of these numerical exercises. And what we could do now is to go back, and if we make this smaller and smaller, as people said, what we would expect then, and we see that here, right? The oscillations, I went to 20. So we would actually need to go over a much, much larger time in order to see this motion to die out. Now, there's one thing which we're going to do next week when we do the mathematical derivation. If I put gamma equal to 1, we are going to get a motion which looks like this. That looks interesting, or rather it looks pretty boring. So in this case, what would you say about the motion? What kind of, yeah? No, I think, yeah, let's do that. Okay, yeah.
The damping is so high that it just slams to a stop at about the side.
Yeah. So which kind of mathematical function would you think drives everything now? Exponential. And this is what we're going to see. And if I make it gamma larger and larger, it's going to be an exponential decay immediately. And this is what you see here. There's basically no oscillation in this case. Yeah?
Will this be considered critically damped?
Yes. So when I put gamma equal to 1, this is called critical damping. When I make gamma larger than 1, this is going to be called over damping. The case you saw previously where you had the oscillations, that is normally called under damping. So this is the way we would typically label these kind of systems. This is excellent, folks. Now I'm going to do one thing more, which is also pretty fun. And we are going to, actually the analytical solution is a little bit more greasy. It takes some kind of exercises in math manipulations. But numerically, we can just now, you can think of adding a force, right? So you don't want to have the system which gets damped, but you want to add some kind of force which just keeps it oscillating till infinity, right? So if we go back to the whiteboard, let's now do the final numerical experiment here and look at a case where we now change the equation So let's bring that up. So suppose now, so we saw that we could have something like this underdamping. And in that case, we saw something like this for x as a function of time. We could start here, it goes down a little bit, and then it oscillates a little bit, and then gradually it comes down to 0. Now, suppose we would like this thing to oscillate back and forth all the time. We know that there is a friction term, so we could add an external force. And this could be a force which depends on time, so an f of tau. And let's just call this an f0, which is the magnitude of the force. And we could say this is a cosine. So this is an oscillating thing. So we want our object to oscillate, right? So if we then can apply an external force, which has the oscillatory motion, we would expect the object to oscillate, right? So we would just have now some kind of frequency multiplied with this tau. And depending on the value of this frequency, this object may oscillate strongly or less strongly, and depends also on the strength of the force. So if I add that, my equation now is going to look like a d of x of d tau and plus a 2 times gamma of dx d tau plus x. Now I have to be a little careful now because I put in a force. So this should be an f tilde here. So it means that I have divided by the mass, and I have actually made these quantities here so that they actually only have dimension length. And this would now have, so let me just bring this one down here. So this is multiplied with a cosine, and it has an omega times t here, like this. By the way, just a kind of a question. The argument to cosine, what dimension should that have? Do we have a, does an argument of function have a dimension? Can I calculate cosine of 10 meters?
Yeah,
Cosine of meter? Doesn't make sense, right?
Yeah.
So the argument to a function has to be dimensionless. So that means that if I made this tau dimensionless, I have to be a little bit careful with this omega here. Actually, this omega is going to be a scaled omega, which is divided by this natural frequency omega 0. So these are technicalities we will come back to. But let's go back to the program now. So we could, in the program, the only thing we need to do in the program is just to add this force, period. That is just few characters in the program. So let's do that and see what happens. And this is getting close to the end of the day. So let's just do this as the last thing today. So we go back to the program, and the thing we're going to do now is simply to add the force. And let's say that this force is 5 as a constant. And then we multiply with cosine. And then we have t of I, like this. That's the only thing we need to do. That's the strength of you having a general program. And you want to add new features. And this is the only thing. It's so neat, isn't it, right? And now we can start playing around and see what happens. Aha. Let's make this, give it a longer time. Let's give it 100 dimensionless seconds. And perhaps we change, we could bring in some period here 2 times. Let's see what happens. Yeah, looks like this. So now it's going to oscillate all time, right? Let me see if I can again trigger your intuition. What happens in the beginning? in the very beginning here. I have some bad hearing here with it. I have this AirPods, and sometimes when you guys speak, I have some problems hearing here.
Is it because the force is stronger than the force of gravity?
Not exactly. Just think of this, you have friction in the beginning. So the very few moments, what do you think happens in the very few moments here? Yes, exactly. So in the beginning, this force is fighting against friction and the natural frequency of the system. So, and this you see in the beginning here, and then after some few seconds, it's the force which takes over. And then this object is going to oscillate with a frequency dictated by the force which you applied. So it needs some time to overcome the friction which you have, and then it kicks in properly, and then the system stays with that the rest of the time. So next week, we're going to derive the analytical solutions and see that our intuition fits with the analytical solutions. I think this is a cute way of showing physics, of playing around like that. Okay, folks, feel free to hang around if you want, discuss the midterm. I'm just going to put off the recording. That's enough. Just going to put off.